For nå skal vi over til del 3. Nå det over til innovasjonsbiten. For selv om vi har hørt i dag at det ikke så mange bestanddeler i betong, altså vann, sement og tilslag, så innovasjonsmulighetene uendelige. Jeg selv ingen betongekspert, og selv synes jeg det har vært veldig gøy å gjøre litt research til dagen i dag. Og her har jeg funnet både at urin foreslått i stedet for vann for månebetong, hvor da på månen det begrenset med vann, så der måtte man innovere på det. Og at det også har blitt brukt kokain som tilslag etter større beslag i Ecuador. Ok, de som kommer og presenterer i dag har kanskje ikke like bra clickbait som urin og kokain, men det ikke mindre innovative av den grunn. And the first concrete innovation pitch today is Paebbl. Andreas Saari is the co-COO and co-founder of this exciting technology. Paebbl turns CO2 into a cement substitute. And the cement substitute is a substance of olivine rock, rock, who has reacted with CO2 in a high pressure process. The resulting material can be used as a key ingredient in concrete, where it locks the CO2 away from the atmosphere for thousands of years, even beyond the lifetime of the building. So let's learn more about this process and the key concept of Paebbl. Andreas, the microphone is yours.
Thank you. Hello, everyone. Thanks for the opportunity to be here. I will just do a quick click check and see that the slides work. Perfect. All right. So let's talk about how we can make the ways we produce some of the key ingredients in our built environment future-proof. So first, what do we mean by future-proof? Well, we all know, of course, what the problem is. The problem with the way we're currently making materials is that we are being very wasteful with both the energy that we're using and the raw materials that we're using, where oftentimes, first of all, we're burning fossil fuels and releasing a lot of CO2 into the atmosphere that we all know that we must transition out of. But also, we're using raw materials and feedstocks of which we only use one small part in the finished product, and the rest goes to waste. And I'm going to look at a very specific example of that, which we all know very well. Just getting on the clicker again over here. Before looking at the example, we of course all know what this way of making materials has resulted in, which is, hold on, I need to reload my slider clicker. There we go. This is what it has resulted in. So we don't need to take too long to look at that one. But let's look at a material that is very close to all of our hearts in our works, which is the key component in concrete, the glue, the binder that keeps it all together, cement, and the traditional way of making cement, and what we could do to change the way we make cement, because it has a lot of problems. So if you look at the traditional way of making cement, you see two major data streams over here. One of them is the energy demand for each process step, and the second one is the amount of CO2 generated as emissions from each processing step. So we can see that the core part of the problem with making cement is the high temperature kiln, the furnace, in which we are running the key conversion step for making cement. And the key conversion step is turning limestone, which is calcium carbonate. Calcium carbonate is calcium oxide and CO2 bound together into one mineral product. We're turning that calcium carbonate into calcium oxide, which is the key reactive component in cement. There are a few other small minor fractions, but this is the key factor both from a climate impact perspective and a functionality perspective. The problem with making cement in this way is that you're being quite inefficient with the way you're making your materials, because you're bringing in 2 tons of limestone if you want to make 1 ton of cement at the output, and you're losing half of your product in the calcination step, in the high temperature kiln. And if we look at, the most immediate options for making the cement production process more green, you might think about electrification. Well, let's just, instead of burning fossil fuels, let's use electricity to power the high temperature kiln or the cooler or the mills or the transportation. Even, if you electrified every step and you used only renewable energy for that, you would still be left with roughly 50% of the emissions of making cement. And that 50% is purely because of the feedstock that you're using, calcium carbonate. So everyone knows in this sector that we must change and we must find alternatives to cement or decarbonize cement in some way. And in fact, it seems that the closer you are to the end consumer or the end customer who's actually interacting with the finished product, whether it's a house or a bridge or a tunnel or something else, the desire and the demand for the material to be sustainable and thus the willingness to pay is also greater. It doesn't necessarily go over the moon, but it is definitely greater than at the mid-market section of this industry, which is the cement and concrete producers, who, of course, we have early adopters who want to change, but they have a lot of incentives to keep doing what they have been doing for many years. Now, let's talk about what we are doing about this. So we're working with a process called CO2 mineralization, where we simply take CO2 that has been captured from industrial emissions, from the atmosphere, or from the ocean, or from anywhere you get CO2 from. We put that CO2 into a high-pressure reactor together with water and together with some ground-up normal minerals. And what happens in that reactor is a reaction that occurs in nature anyway, which is CO2 wants to combine with that kind of mineral to form a stable carbonate mineral, like limestone, which is the feedstock for cement production. Now, what we do with the chemical reactor and the high-pressure reactor is just a radical acceleration to this process, where in nature, this sort of a process of CO2 turning into rock takes typically thousands of years or tens of thousands of years. We can accelerate it to a matter of hours or even minutes in some cases, and thus make it a viable industrial process. And of course, the most interesting part is that the output of this kind of a process of binding CO2 into rock, which is as stable as you can make CO2, is that it's a valuable material that comes out. And it can be used, for instance, for substituting cement. And now, again, I need to re-update my clicker. Pardon for that. So let's have a rough comparison for the traditional way of making cement and an alternative way of making cement. So as said, typically this is a simplified picture, but gives the gist. You have to ship in 2 tons of product into your cement factory to ship out 1 ton of cement. And you're losing 50% of the process, and you're burning fossil fuels to lose that 50% of your product. You're left with 1 ton of end product. Now, instead, if we use a different feedstock, like olivine, for instance, and not lose the CO2, but add the CO2 to the olivine to activate it, to make it cementitiously active, you're left with 3 tons of output product, which is not a one-to-one replacement to OPC, but it performs very interestingly. In fact, we have been doing roughly 7 generations of recipe development at this point with our product. I'm just stealing the clicker here again. By replacing first just some parts of the sand that goes into the concrete, but then increasingly replacing the Portland cement that goes into it. And we have replaced now, we're still getting very strong concrete at more than 50% substitution of the cement. More published numbers coming later on, not just yet. As a company, we're based on 18 years of research in the academia, and we're still very young. We were started 2 years ago. We started with a prototype, then outsourced production with a university partner. And since this May, we have been producing 1.5 kilograms of this product in-house. We're just commissioning the machine on the right, which gives us 150 kilograms per day. And a year from now, we should be at 1.5 tons per day. And after 2 years from there, in a commercial scale facility in producing this material. Now, let's look at the scalability on a global scale. Is this only going to be a niche solution in some corners of the world? No. You have the right feedstocks everywhere or in every continent. And you definitely have CO2 everywhere where you want to go, which is the other key feedstock. Our team is quite experienced. We've done this before, scaled up multiple hardware and software companies, scaled up technologies. in big company contexts as well. Our VP engineering is a guy who just spent 20 years at ExxonMobil, scaling up and deploying different kinds of technologies. And the team is growing. We're roughly 25 people now, so the numbers are actually a little bit outdated. We are currently working with a limited number of early partners who might be interested in testing this material. And now that we're increasing the production capacity from 1.5 kilos a day to 150 kilos a day, we can unlock much more potential for different pilots and tests. So if you're interested, shoot me an email on that front, and happy to take any questions. Sorry for the 40 seconds extra.
Thank you, Andreas. Are you in contact with any projects in Norway?
Yes, we are close in contact with one particular architecture firm called Oslo Works. We have been, well, in conversations with them, preliminary conversations at this point, about multiple construction projects that they have in the works. We have also had a dialogue with Sintef and their concrete experts for quite some time, and likely before selling our material to the Norwegian market at scale, we would do our performance testing and certification with Sintef. So there's a dialogue ongoing, and of course, for us, what makes Norway very interesting as a potential location for the first commercial scale plant is the fact that you have the feedstock that we want. In fact, Norway has the biggest mine in the world currently for olivine that is currently being operated. So the market could be very suitable for combining, taking care of some CO2 with some olivine to make a future-proof version of the cement that you might be using. By the way, that cement could also be combined with biochar or biokul.
Yes.
We're also doing tests on that front, so you could push the CO2 footprint of your concrete even deeper down into the carbon negative territory.
Very nice, Andreas. Thank you so much for your time.